We started the new lesson in matrix theory part 3. Of course, let me just review very quickly what we learned last time. We learned that we can also add and subtract matrices, and then we learned that if we have two matrices A and B of the same size, having the same number of rows and the same number of columns, then in principle we can add them and we can subtract them. Yes, and the addition and subtraction was defined in a very natural way, entry by entry. I will take one entry from one of them and add it if I want to add, subtract it if I want to subtract from the corresponding entry of the other matrix. Yes, that was exactly what we defined for the addition and subtraction of two matrices. For example, here you can see some examples. These are so simple, I prefer to type them, not to spend so much time on this because they are very simple, but if I want to write, it takes time, and that is not very valuable, I think. So if you have two matrices of the same order, here both of them are 2 by 2 matrices. If I want to add them, as you see, I am taking the first one, adding it to the first one, and write it as the first entry, and I will continue for the other entries, and then I will get these numbers, and then I simplify, and final answer is this. Yeah, it's very simple. Here again, can I add these two matrices? Yes, because both of them are 3 by 1 matrices. Yes, and then I add them entry wise, component wise, and then if I add them, the answer would be this. Here are two examples of subtraction of two matrices. Can I subtract these two matrices? Yes, both of them are 2 by 1 matrices, so the subtraction is also a 2 by 1 matrix, calculated like this. I will take 1 minus 2, and I will take 3 minus 4. And the same story here. I have 2 by 3 matrices here. I want to subtract them, so I will subtract them component wise. For example, this one, 3 minus 3 that you see is here, becomes 3 plus 3, so that is equal to 6. And then you continue with the other ones. And then here you see an example of two matrices. If I ask you what is the sum of these two matrices, you should say it's not defined. They are not of the same order. The same for subtraction of these two matrices. The difference of these two matrices is not defined either. Okay, and then I think this is also a very simple example. What's your opinion about that? Hopefully you remember what are these words. In matrix theory they are important. So what do you think would happen here? The sum and the difference of two upper triangular matrices are, what can I write here? Is there something that we can write? Do you remember upper triangular matrix was a matrix like this, so that if this is the main diagonal, everything below the main diagonal is 0. So if I have two blocks of matrices, both of the same triangular type, it is very clear, hopefully, for you. Of course, you can prove it rigorously, but this is so obvious, let us just write it down. If I have two upper triangular matrices and I add them, because I'm going to add them component-wise, entry-wise, so this is clear that these zeros will be added to corresponding entries here, which are also zeros, so they will remain 0. Yes? So it means that the sum of two upper triangular matrices is again an upper triangular matrix. Please, if you have any questions, you can interrupt me. Yes, please.
Is there any guarantee that the slope of an upper triangular matrix, like how do we know it's an upper triangle or undefined maybe?
No. Of course, I am just talking about defined ones. If they are undefined, that's not defined. Yes. It might be a little bit careless, but I was assuming that they are defined. And the same story, I think you can immediately see that if I add or subtract two lower triangular matrices, it becomes again lower triangular. And the same thing for diagonal, yes. Of course, they have to be of the same order. Okay, that's right. Then we had this before, if you remember, that was the last problem we solved last time, and I think that's also very obvious. And I talked about that, okay, this addition is not the normal addition. This is something that we learn new, but this addition is just the normal addition because trace of a matrix, the sum of the diagonals on the main entry, is a number, and the same here. So I am adding two numbers here. So the summation on the right hand side is just a normal summation between two numbers, but the summation appears here is a new summation. This is the summation of two blocks of numbers of the same order, or in other words, two matrices. And I think that was simple, so if you have forgotten, you can go and review the previous video. Okay, now we can start the new lesson. They are very simple, so this lesson is actually very simple. The interesting thing starts from the next session. But these are necessary, you have to know about these definitions. The first thing that we want to talk today is opposite of a matrix. Okay, and exactly like numbers, the motivation is like that. The opposite of a matrix, any matrix, even rectangular matrices, the opposite of a matrix is denoted by minus a. Again, this is an abusive notation. Yes, it is different from saying minus 2. I am putting a minus sign for a block of numbers, matrices, and then so this difference, this negative sign that I put here is different from the meaning of this negative sign that I put for example, 2. It's defined to be, it's very natural, I think, again. If you want to define it, you define the opposite of A to be a matrix of the same order. Yes, so the order is not changed, but any entry in this new matrix is the opposite to the corresponding entry of the original matrix. Yes, for example, if I have this matrix 2 by 3, if I ask you what is minus a, what you do, you multiply each one of these entries by a negative sign. So clearly this becomes negative 1, the next one becomes positive 2, and then so forth. Yes, this is very simple. So that is called the opposite of a matrix. And now the theorem here, properties of matrix addition, is actually, it seems trivial. Of course it is simple, but it is not trivial because these operations are not the operations that we used to. Yes, this is just not a normal addition. It is the addition that we define for two blocks of matrices. A priori, in principle, there is no guarantee that because, for example, addition of two numbers is commutative, the addition of two matrices of the same order is also commutative, even though in your head you can immediately imagine what's happening and then conclude that yes, the addition of matrices of the same order is also commutative. Yes, and the same story for associativity. But these need to be proven. Okay, so let us just prove one of them. So you see, first of all, up to this point, you don't need to memorize any new formula because the sum of two matrices is commutative. The sum of matrices is associative. If you add the zero matrix to any matrix of that order, the answer, of course, becomes the same matrix. And if you add a matrix to its opposite, it becomes the zero matrix of the same order. Okay, so whenever this addition is defined, the addition enjoys these properties. Let me, for example, try to prove number 2, that is associativity. So what does associativity bring for us? It tells me that if I want to add more than two matrices, say 3 matrices here, A, B, and C, it doesn't matter how I prioritize these two addition operations. You see, if you don't look at the pair of brackets, you have two addition operations. And it tells me when an operation is associative, it means that prioritizing these operations are not important at all. So let me immediately tell you an example of an operation which is not associative. So for example, I will write this and clean it because we don't need it that much. So in the exam, for example, for a primary school students, if I just write this in the exam, they probably will not complain. Yes, they would say that, okay, it doesn't matter how I interpret this. Do I interpret it in this way or I interpret it in this way? The answers are the same. Yes, because this gives me 5 plus 5, the answer is 10, and this gives me 2 plus 8, which is 10 again. So even though in the intermediate steps I'm getting different values, but finally I will get the same value. This is why the reason this is working is because addition of numbers is associative. But if I give this to primary school students, they will not be able to answer this. And that is my mistake. Because if I ask calculate 2 divided by 3 divided by 5, I am actually again facing two same operations. Yes, this one and that one, they are the same operations. But here, it completely depends how I prioritize one of them over the other. Yes, and this means that whenever this happens, that an operation is in a way that if you want to do a bunch of them, it matters that how you prioritize these operations. This means that your operation is not associative. So working with operations that are associative is much simpler, yes, because we don't need to be worried about how to prioritize the operations. Okay, so here, because if I interpret this in this way, prioritize the first one, this will give me 2/3 divided by 5, and if you calculate it, it is 2/15. But if I prioritize the second operation first, then it becomes 2 divided by 3/5, so the answer becomes 10/3, and then you see that they are not equal. So it is very important to understand what the meaning of associativity is. Okay, this is very important. Okay, now we want to say that no, don't worry, the addition of matrices also enjoys that property. So it means that if I have a bunch of matrices added in a string, in a list, it doesn't matter at all how should I add them, okay, which one I prioritize. And the good point about commutativity tells you that you even don't need to bother about the order that you are adding them. So you can group them in different groups. You can just interchange any pairs of them. It doesn't matter at all. Okay? So that's a very nice operation. But immediately next time, hopefully, we will see that the product of matrices loses this property, but still, in a very nice and strange way, preserves this property. So we will lose one of them when we go to matrix multiplication. Okay, with this introduction, let us start now proving this. Okay, so for example, I just want you to learn how to prove things. Yes, you want to prove this is equal to that. What is on the left-hand side is a matrix. What is on the right-hand side is a matrix. So if I want to show the equality, it means that I am showing the equality between two matrices. So I have to respect the equality of the definition of the equality of two matrices. First, I need to show that they are of the same order. This is not a big deal because it is in the problem. It is mentioned that all A, B, and C are of the same size. So it means that the sum has the same size. Again, I added with this one, it will give me the same size. So it is clear that the right-hand side is also of that same size. So I need to show that each entry of this is equal to the corresponding entry of this. So for definiteness, let me write this. Proof of, for example, 2. What we said for definiteness of discussion, let the order, so let all of them, all matrices be of order, say m by n, and let I be between y1 and m, for example, and j between 1 and n be integers, or of course natural numbers. We show that the entry, the ijth entry of the left hand side is equal to the ijth entry of the right hand side. Oops, sorry. I don't know why the fan of this I hope that this is not very disturbing for you. Usually I don't even hear the fan of my computer.
The microphone is picking up the fan, so
it's okay. Is it disturbing?
No, we can't hear it.
Ah, okay. We show that this is correct. Okay, how should I do that? I will start with the left hand side again, as usual. So if I ask you, what can I write instead of the left hand side? You say that I can assume that this is a matrix, let me call it D, and this is another matrix C. I am interested in the ijth entry of this sum. Of course, you know what is the meaning of this. It means that I need to take the ijth entry of the first one and ijth entry of the second one. Oops, this is not a good way. So let me put this in respective notations and conventions. So that is it. But now, if you ask me what is the first one, again I can use the same definition. So if I want to do this operation, what I have to do, this is just, by the way, this is a normal addition. These additions are not normal, they are matrix addition. These are number additions because this is at the end a number. This is the ijth entry, and that is also a number. If I want to do this addition, I need to know what is this guy. When I calculated that one, then I can add this one, add it to the next one. So it means that if you ask me what is the first one, I would say that again, according to the definition of the summation of two matrices, this is this one. And then of course, I will have this one again. But now, I hope that you understand that's not a circular argument. I use associativity to do this. You might say that, okay, I am proving associativity, so how do you use it? What's your answer? You understand what I mean? I want to show that. What?
One is for it's different types of associativity. One is for the old operator. This one is.
Yes, that is for just normal addition, exactly. So you see that. Let me just write it down here. Associativity of addition of numbers. Yes, so exactly. So these are different levels of associativity. We want to show that this is the matrix addition is associative. What we have used is not the same thing. I have used the associativity of the addition of numbers. So this will tell you that this highly depends to the associativity of real numbers, okay? If the associativity of real numbers is gone, so you will not have this property, okay? Exactly. So then the rest of it, I think, is completely clear and easy. So here, I will just write I will just write Aij. For the second one, I can write it as B plus Cij And then again I can write it as a plus b plus c, the whole expression ij, and that is the right hand side. Okay, so that was the only thing that I wanted to teach you. So this is very, very simple, but I wanted you to understand the reason associativity of the matrix addition is there is because of the associativity of the just normal addition. So this is why every property that you can see here is because the definition of matrix addition is very similar to the addition of normal numbers, so the properties of addition of matrices should be expected to be more or less the same, and then this theorem shows that you don't see any deviation between these properties and the corresponding properties for real numbers. Any questions? Okay. Now we go here. Another theorem which was correct and very helpful when we were dealing with number addition was additive cancellation rule. Additive cancellation rule is that, for example, if you want to solve an equation, you can say 2 plus x is equal to 2 plus 5. Yes. If I ask you what is x, you can say that, okay, I eliminate these twos from both sides and I get x is equal to 5. And of course, what is the reason that you can do this? It becomes clear. We will do the same thing here. We want to say that the same idea works if you have matrix addition instead of number additions. If you have a plus b, matrices of the same order, is equal to a plus c, matrices of the same order. If that is the case, you can simply ignore a from both sides. You are canceling an addition, so this is why it's called additive cancellation rule, and then you can conclude b is equal to c. Okay, so why is that true? Let us do this. I want you to understand this because this way of thinking rigorously a little bit is very important if you want to be good in mathematics. So let me write proof here. So how should I, by the way, prove this? I would say that, okay, you are telling me that a plus b is equal to a plus c. So you are giving me two equal matrices. And then I can add I can add the same matrix to both sides, yes? So it means that minus a plus the matrix on the left has to be equal to minus a plus the matrix on the right. Okay? Because first of all, I know that these two matrices are the same, and you are telling me that these two matrices are also the same. So this is clear that this sum and this sum should be the same thing. But now I know that matrix addition is associative, so it means that I can take the pair of brackets from the second pair and put it around the first pair. So if someone asks you why this step is correct, you need to refer to the associativity of matrix addition, which is number 2 of the previous theorem. Yes? And then again, we had another part of that theorem that any matrix added to its opposite is the zero matrix. And on the right hand side I will have also this. But again, it was another property, so that the zero matrix plus any matrix is the matrix itself, and then we are done. Okay, so if you see, if I want to go back, so remember these number 1 is not used, but number 2, number 3, and number 4 here are actually used, otherwise this theorem was not working. So it is very good to understand what is behind this very simple conclusion. Yes, so from here to here, it's number 2 associativity, and from here to here, it is number 4. Yes, it's number 4, and from here to here, it's number 3. So you see, this very simple argument is based on all of these arguments. So if one of them is gone, so this will not survive. Another theorem is actually very simple. So do you remember, if I wanted to solve this equation for numbers, I immediately take a to the right and make it negative and write b minus a as my answer. Okay? This is also true for matrix addition. If you have an unknown matrix and you want to find it from this equation, it's very simple. You just move a from the left to the right, but you need to remember you have to change the sign. As simple as that. So this theorem claims that, or asserts that, A and B matrices of the same size, then the matrix equation in which X is an unknown matrix has a unique solution, and that solution is this. By the way, if I want to show that there is a unique solution, if you want to be very rigorous, you have to show two things. First of all, you should show that this is indeed a solution, and then you show that this equation cannot have more than one solution. So this you need to show this is the meaning of a unique solution. Okay, so if I want to prove it again, I would say that we first show that b minus a, x equals to b minus a is a solution. How should I do that? Very simple. I should show that this satisfies the equation. So what should I do? I need to start from the left hand side. A is a. Instead of x, I put what is proposed to me, and I will try to simplify that. But you see what is happening. First of all, if I want to write every step, I have to think in this way. B minus a is actually b plus minus a. And now, what I can do, I can use associativity and put the pair of brackets around the first pair, and then minus a becomes alone. And then I use commutativity to interchange these two, and then have it minus a. Again, I use associativity to put this pair of brackets around the second pair. Then I use this fact that a plus minus a is 0, then I use this fact that b plus 0 is b. So you see, for this very simple calculation, especially if you are interested in programming and things like that, so you need to see which the operations, if you really need to understand, if you want to go from here and show that this is the answer, what are the main properties for the operation needed. So you see, for this argument, associativity, commutativity, and this the identity element, the opposite of a matrix with itself is equal to the 0, all of them are needed. So all of them actually, all four of those theorems, all four parts of that theorem actually used in this very simple and apparently innocent proof here. Okay, so that is the reason that I am talking about this, because otherwise problem solving at this level is very simple, we will see. Okay, but this problem is not finished because we want to show that this is the unique solution. Okay, so how should we show that? Let us use proof by contradiction. Okay, uniqueness. Okay, so I would say that, assume that x1 not equal x2 are both solutions, yes? So then what does it mean? When you say that x1 is a solution, you can conclude that it satisfies the equation. So it means that a plus x1 is equal to b. When you say that x2 is a solution, this means that this also satisfies the equation, yes? So it means that a plus x2 is equal to b. But now I see that the left-hand sides are both equal to the same matrix B, so I can conclude that a plus x1 is equal to a plus x2. But just right now we prove the additive cancellation rule. Yes, and then I see that I can use it immediately here. Why? Because this matrix is equal to this matrix, and then this matrix is in common. So by additive cancellation law, I can cancel this and conclude that x1 is equal to x2, but that is contradiction because I assume that these are distinct solutions. So if you assume that there are two distinct solutions, then it gives rise to a contradiction, because on the one hand you have to admit that x1 is not equal to 2, and logically at the same time you have to admit that x1 is equal to x2. Okay? Of course, I will not give these kind of questions, but I want you to understand. These simple arguments are not that trivial. You need to understand if one of them, which one of them is gone, then the theorem is actually gone. So you see that all those properties are somehow needed when you want to do this very simple operation. Just moving a. Exactly, if you want to prove something like this for numbers, you will follow exactly the same ideas. Okay. Okay, so here, for example, this is not a very big deal, so you know how to do that. So if I want to answer this question, I am going to solve this equation for x. So the answer is that I move this known matrix to the right and change the sign. Yes. So I will keep this on the right, and then I would write minus 1, 2, 4, minus 5, and then of course you can simplify that. Minus 2 minus 1 is minus 3, 3 minus 2 is 1, and then it is 1, and then it is 13. So as simple as that. That is the solution of this simple equation. Okay. Any questions? Yeah, they are very simple, but they are actually very important. Okay, the next operation that we want to define is called a scalar product. Usually in linear algebra, so this matrix theory in the higher level mathematics is actually part of a subject called linear algebra. And in linear algebra, numbers are called scalars. Okay. So when we say a scalar product, it means that I am going to multiply a number to a matrix, or a matrix by a number. Okay. So the definition is again exactly very natural. So what is your guess if you want to multiply a number by a matrix?
We multiply all the entries in the matrix.
Exactly. That is the most natural one, and we start. And then, by the way, this natural one is not very. So, for example, we will see that I don't know what is your idea about how to multiply two blocks of matrices naturally. Might be you also think that multiplying component by component is the most natural one, but you see that mathematicians has chosen to define matrix multiplication in a different way. They of course have an idea why they want to do it. I don't know if we can cover those. This is a little bit higher level. Might be I can motivate you a little bit, but not that much. Okay. Anyway, again, another operation we are learning. So we learned how to add two matrices. We learned how to subtract them. We learned how to put a negative sign and make the matrix opposite. But now we want to learn how we can multiply any number, any real number, to our matrix. And that's very simple, as you told, is this A. Assume that A is a matrix m by n. Again, you see it's not a square matrix. It can be even rectangular matrices. And R be a real number. The product of A by R is denoted, usually we put R first on the left. R times A, and it is defined exactly as you define. This, you see, it means that the entry on the ith row and jth column of this matrix is this. If you compare it with this one, it has been multiplied by R. And because this is happening for all I and j's, so it means that what you said is completely correct. Another way of writing that is this one. R times A, again, this R times A, ijth entry, is equal to, you go and find the ijth entry of A and multiply it by R. Again, this operation here is new. This operation here is the old one. Yes? Because here I am multiplying a number by a block of numbers, a matrix. Here I am multiplying a number by another number. So again, you see that's also a little bit of abusive notation. So I don't know how should I give examples. They are very simple, of course. So if I have this matrix, I multiply it by this real number. It means that I need to take a square root of 3 and multiply it everywhere here. Clearly, when I multiply it here, it becomes 3. If I multiply it here, it becomes 3 over 3, which is 1. If I multiply it here, it becomes minus 1, and etc. Yes? If I multiply it here, it becomes 3 times 3, which is 9, and continue. And now that we have learned the operations of addition and scalar multiplication, sometimes we can combine them. For example, I have given this example for this purpose. Yes? If these matrices are given, I don't think that's a big problem to understand what to do. So 3a means that I have to multiply 3 inside my matrix. So it becomes 3, 6, 9, minus 12. And then I put a negative sign, I multiply 4 inside. So it becomes minus 12, 8, 4, and 0. And then I start subtracting them. So it becomes 3 minus 12, 15, minus 2, 5, and minus 12. As simple as that. Okay, any questions here? I'm not asking because they are very, very simple. Okay. And now let us solve this problem. Let A, B, and C be these matrices. Determine the real numbers alpha, beta, and gamma such that alpha times A plus beta times B plus gamma times C is equal to 3i. And of course, I told you that I is always reserved for the identity matrix. We have infinitely many identity matrices, of course, of different orders, but needless to say that this I refers to the 2 by 2 one. Yes, because if I have 2 by 2 matrices and I multiply them by numbers, they remain 2 by 2, and if I add 2 by 2 matrices, again it remains 2 by 2. So if this equality is supposed to make sense, the right hand side should also be 2 by 2, so this means that this I is a 2 by 2 identity matrix. So what I want to do, I just start writing alpha A plus beta B gamma C is equal to 3i, and then what happens? Alpha times A means that I have to multiply alpha in all the entries of A, so it becomes 2 alpha, 0, 0, 3 alpha. Yes, and then I go to this beta times B, which is 3 beta, 0, 0, 2 beta. Yes, and, oops, I don't know why sometimes this feature doesn't work. And then plus gamma is 0, 3 gamma times 0, 0. And on the right hand side, the identity matrix, do you remember, is 1 and 1 on the entries. When I multiply that, those become 3, but these remain 0. Yes, so what I have used is that I is actually this matrix. Okay, and then what I can do, I can collect the left hand side into one single matrix. So this one plus this one plus this one becomes 2 alpha plus 3 beta, and then the same becomes 3 gamma, the next one becomes 0, and the next one becomes 3 alpha plus 2 beta. This is supposed to be equal to 3, 0, 0, 3. So this gives rise to a system of equations. So 2 alpha plus 3 beta is equal to 3, 3 gamma is equal to 0. Of course 0 is equal to 0 is already satisfied, and then I will have 3 alpha plus 2 beta is 3. So this, first of all, this immediately becomes clear that gamma is 0, and then you need to solve the system. For example, if I add them 6 over okay, so let me, for example, write it somewhere so that I can solve. So here 2 alpha, let me do like this. There is no enough space here, so let us do like this. If I want to get rid of one of these variables, I will multiply the first one by -2, for example, this one by +3, and I add them. This becomes -4 alpha, this becomes 9 alpha, and I subtract them, it becomes 5 alpha. On the right hand side it becomes -6, +9. -6, +9 is 3. So alpha is 3 over 5. Yes? Alpha is 3 over 5. Okay? And then alpha is 3 over 5. I put it somewhere here to find beta. So let me write here. Beta is 3 minus... No, 3 beta is 3 minus 2 alpha, which is 6 over 5. This becomes 9 over 5, so it is 3 over 5 again. Yeah, so beta is 3 over 5. By the way, I did it very stupidly. It was simpler because both of them are equal to 3, so 2 alpha plus 3 beta is equal to 3 alpha plus 2 beta, yes? So this means that alpha is equal to beta. So then it becomes very clear that this is the answer. That was simpler, I think. So these are the numbers that we are supposed to find for this problem. And you see that the problems are very simple at this level. Okay, so here we can extend that theorem. So what happens if I multiply, by the way, if I go a little bit fast here. If I ask you what is the trace of R times A, can you connect this to the trace of A? So, for example, you have a matrix A, B, C, D. The trace of this matrix is the sum of these two numbers. Now let me multiply it by R. It becomes RA, RB, RC, RD, and now I take the trace. The trace would be the sum of these two numbers, so it becomes RA plus RD, but it is clear that I can factor R because these are numbers, and this part is actually the trace of the old one, so this becomes R trace of RA. So it is clear that trace of R times A is equal to R. Of course that was not a proof, but that was just the motivation behind that this is true. Okay? So if I want to prove this rigorously, what can I do? I can start from the left hand side, and I need to define the trace first. What is the trace of this? S and R are numbers. S and R are real numbers. A and B are square matrices of the same order. Here we have to respect that the trace makes sense only for square matrices. So here, if I ask you what is this, let me write this. I should start, let matrices be of order n. Okay, then this trace becomes equal to the sigma of R times A plus S times B, I goes from 1 to n. I hope that you are now familiar with this way of writing. Yes, why I write I? Because I am adding the elements on the main entry, and on the elements on the main entry actually have the same indices for row index and column index. But now, according to the definition of addition first, be careful, this becomes RA II plus SB II. So you need to respect these things. Why this is correct? Because of the definition of addition of two matrices. This addition is not the matrix addition, but this addition is a number addition. And then I goes from 1 to n. And now we use the definition of a scalar product to be able to pull R and S out. Yes? So then it becomes R times A I plus S times B I. I goes from 1 to n. But now, because of the properties of sigmas, you can write the first one. You can decompose this sigma into two sigmas. Yes? But now, because of another property of sigma, this R is not doesn't depend on the counter. So as far as this sigma is concerned, R is constant. As far as this sigma is concerned, S is constant. So I can pull it out. So if you want to write all the details of the proof, this is the way that you have to write, even though this seems very easy to imagine immediately. But now if I ask you, what is this one? The answer is this is the trace of A. And what is this one? This is the trace of B. So this becomes R times trace of A plus S times trace of B. Okay? So here, this multiplication and this multiplication are new multiplications, and this is the new addition, but this addition is the old one. These multiplications are also old ones because they have been done at the level of numbers. These are done at the level of matrices. Okay, any questions? We finished. We go to another very important theorem. That is called, actually this is the theorem for properties of this multiplication that we learned. There is no big surprise there for you either, so you don't need to be very observant when it comes to this, because more or less everything is a very natural operation. So of course you expect that if you multiply your matrix by 1, it should be the matrix A. And now you can imagine multiplying a matrix by 1 means that I take 1 and multiply 1 by the entries. Nothing will change, so you will get your matrix back. And then if you multiply the number 0, appreciate the difference between these symbols. So if you multiply the 0 number by any matrix, it becomes the 0 matrix of the same order. It's clear. And now if you take any number that you like, but you multiply it by the 0 matrix, the answer is again the 0 matrix. You see, even in this case and this case, both of them are 0 matrix because the output of the scalar product is not a number, is a matrix. And now, of course, this was also possible for you to guess, because if you take your matrix, the entries of your matrix and multiply it by a negative sign, it means that you are multiplying each entry by the negative sign, so you get exactly what we defined for the opposite matrix. Okay? And these three properties are also important. For example, let me tell you, I haven't called this associativity, even though it seems like that. Yes? When I have three numbers, so you see, when I say associative, it means that the operations should be of the same kind, of the same type. Yes, here, for example, I can say that this is associativity for numbers. Why? Because this addition is the same addition that you see here. Both of them is the same are the same operations. In that case, when I take the pair of brackets from one of them and put them around the other one, I call it associativity. For example, even in numbers, I write this, for example, assume that A, B, and C are numbers. If I write this is equal to this, which of course is, then I can call this again associativity. Because this operation is the multiplication of two numbers. This operation is exactly the multiplication of two numbers. So these are of the same type, and this tells me that I can take the pair of brackets from one pair and put it on the other pair. Even though this seems a little bit like associativity, but if you understand what I said, it is not associativity. Why? Because here R dot S, if I put a dot for product for all of them, then this dot and this dot are different dots, yes? This dot is the product between two numbers, then I get a number. After that, I want to multiply it by a matrix, so the second dot is the product of a number by a matrix. It's a scalar product. This is just a normal product, that's a scalar product. So this is not associativity, even though it seems like associativity. But it highly depends to associativity of the normal product. Okay? And then again, for example, here, these kind of things, do you know what are these type of properties usually called? Yes, what are they? They are called distributive, yes? So the distributive is okay. So even if you distribute, you have A dot B plus C. So what happens? This tells you that I can distribute this product inside. It becomes A dot B plus A dot C. Yes? That's okay. Yes, that's okay. So because this operation is between two numbers, that operation is also between two numbers. So that is called as distribution. So here it means that I can distribute R inside. Yes, I can multiply R by the first matrix. It becomes a new matrix. I can multiply R by the second matrix. And this operation is the multiplication of a number by a matrix. These operations are also the same. This operation is addition of two matrices. This operation is also the same. But here, what do you think? Can I call this distribution again?
Yeah.
No, because you need to be careful here. What is this addition? This addition is between numbers, but this addition now is changed. This addition is between two matrices. So in distribution, if I write this, for example, let me write it in that way. If I write B plus C dot A, on the right hand side I say B dot A plus C dot A. These dots is the same dot. This addition is the same addition. Then I can call it a distribution. This was the case for this one, but not this one. So technically I cannot call this distribution, because this is the sum between two numbers, but this sum is a different sum. This is the sum between two matrices. Even though it looks like distribution, but we cannot call this distribution. But of course it is highly connected. It's actually interconnected to the distribution for numbers. Okay? So if you don't mind, let me just take this one and prove it, okay? To see how this goes. If I want to prove number 7, let me assume that for definiteness of discussion, let A be and an m by n matrix. Okay? This is clear that the left hand side remains m by n, the right hand side is also m by n, so these two matrices match from the order point of view. So what I need to do, and I would say let I be some number between 1 and m, and j between 1 and n be integers. Of course, natural numbers. Then what we should prove? We should prove that R plus S times A, the ijth entry, is equal to the ijth entry on the right hand side. So according to a scalar multiplication, I should be able to write it as R plus S multiplied by the corresponding entry of my matrix. But now this is the dot between two numbers. This is just the normal multiplication, and that's the normal addition. And normal addition and multiplication enjoy the distribution property, so I can use that fact and write it like this. So you see, it's not a circular argument again. You can see that these proofs depend on, the validity of this proof depends on distribution of multiplication over addition, or for real numbers. Then the first one can be written as this. I made a mistake, sorry, this is not R, this is S. And then the other one becomes S, A, I, J, and then I can, of course, using the definition of addition, I can collect it and write it like that. So if you compare this one and this one, we are done. So this is important to know, but again, nothing to be worried about because everything seems natural. By the way, it is very important. For example, let me write something here for you. What do you think would be this? 2a plus 3a. We take these things for granted and immediately write 5a. Of course, 5a is correct, but this is because of this property. If that property was not there, I was not able to write 5a for this. The reason that I can write 5a for this, because let us take r to be 2, let us take s to be 3. Then this is exactly this expression. This becomes 2 plus 3 times a is equal to 2 times a plus 3 times a. But 2 plus 3 has another name in the world of numbers, and that is 5. So the reason that you can write 2a plus 3a is equal to 5a is because of property 7. Yes? So yeah, you need to respect these things, otherwise. So for example, can I write 2 times 3a equals to 6a? Yes, you can, but because of this property. Yes? If you choose r equal to 2 and s equal to 3, the left hand side is what I want to calculate, but the right hand side becomes 2 times 3, but 2 times 3 has a better name, which is 6a. So remember, if these are gone, these simple calculations should also go away. Okay, and then another theorem is just actually a very simple one. Here, if you have r times a equals to b, r is a number times a matrix is equal to another matrix. If I want to find a, usually in numbers we say we divide both sides by r. We don't divide in matrices. Division by matrices is a little bit hard thing, but of course division by numbers is simple. Division means multiply by the reciprocal. So you see, if I have x equals to, if I have 2x equals to y, if I ask you find x, you can safely write in numbers. You can write this. But in matrices, we do not write a matrix divided by 2. Okay? But there is another name for y over 2, which is 1 over 2 times y. So usually if you want to say a matrix is divided by 2, you should avoid this notation. You need to write 1 over 2 times a. Okay, be careful about that. We do not divide matrices by numbers. Okay, but this is again normal. Why this is correct? Because you are telling me that r is a non-zero real number, what I can do, so let me write the proof here. So you are saying that r is not equal to 0. So this implies that 1 over r exists. I can safely reverse it because r is not 0. Okay, and now you are also telling me that RA is equal to B. Then I can multiply both sides by 1 over R. If you say that these two are equal, then you have to admit that if I multiply them by the same number, still I get the same matrix. Okay, but now let us go back here. Now this comes to our help. Here, this number plays the role of R, and this number will play the role of S. So I can take the pair of brackets and put them around the numbers here. Again, you see that these proofs are simple, but they highly depend on these details. But 1 over R times R is just simply 1, and times A is equal to 1. I made a mistake, sorry, this is not A, this is B. And then this becomes 1 over R times B. But again, one part of this theorem tells you that 1 times A is equal to A, so A is equal to 1 over RB. And then we are done. And there is something also very interesting, very similar to the zero product rule. In the numbers, the reason that I'm drawing these analogies between numbers and matrices all the time, because it's very, very important. It becomes clear in the next lesson. So R times A, so if you remember in the numbers, if I have the product of two numbers is equal to the zero number, you can immediately conclude that either one of these numbers has to be equal to 0, or both of them, of course. Yes? Something similar to these for matrices is this. If the product of a number by a matrix turns out to be the zero matrix, it cannot turn to be the zero number, because by definition multiplication of a number by a matrix is supposed to be a matrix. So if this is going to be the zero, it should be the zero matrix. So this tells you that either the number is the zero number or the matrix is the zero matrix. So that is very similar to the zero product rule for the numbers. Okay? So if I want to prove this, we can prove it in this way. So you see, RA is equal to 0. I want to show that either R is equal to 0 or P or A is equal to the zero matrix. This is the way that I want to prove it. I say that if R is equal to 0, then we are done, because I want to show that either R is equal to 0 or A is equal to the zero matrix. If you say that R is equal to 0, so there is nothing to prove. So let us assume that R is not equal to 0 and show that definitely A is equal to the zero matrix. Is this logic clear for everyone? We want to show that under this condition, either this happens or that happens. I would say that if this happens, we are done. So we show that if this not happen, then definitely this has to happen. Is the logic clear?
Yes.
Yes, so can you translate it in the language of logic, by the way? We want to show that a statement, let me write it with a different color. We want to show a statement P implies a statement Q or statement R. What I claimed here, I claimed that this implication is equivalent to saying what? Can you tell me? You see, that logic was clear for you. Everyone feels somehow the logic. But let us write it. What I told you, you can write it in the logic language. So you see, this statement is of this type. Yes?
Implies not Q and R.
No, yeah, a small mistake. Let me repeat. RA.
In brackets.
No. RA is equal to this. We want to show that this. Oh, sorry. RA is equal to 0. I want to show that this implies that R is equal to 0 or A is equal to 0. I told you that instead of proving this, I say something like this. I say that if you agree with me that R is equal to 0, then we are done. So assume that R is not equal to 0. We show that the capital A is equal to 0 definitely. So you see, do you see that the structure of this statement is similar to this statement? The statement P is this statement, statement Q is this statement, statement R is this statement. Okay, so let me just, there is no time, let me finish this. Yeah, I would think that this is a good exercise. I want to show that if P and not Q, so this was your mistake, you put not Q on the right hand side, then R. So what you immediately understood without actually even doing some calculations in logic means this. If you don't believe in that, you should be able to do it either using the laws of logic we learned or using the table of truth table. Yes, I think that is a good exercise. Please write it down somewhere. Of course I will upload these notes. So this is the way that I want to show it. My statement is have this structure, but I show that, assume that I have shown that this statement is equivalent logically to this statement. So then, instead of proving this statement, I just prove this statement. I would say that RA is equal to 0 and R is not equal to 0. I show that A is equal to 0. If I can show this, because it has this structure and because this is equivalent to this, it means that I have shown my problem. Is everything clear for everyone? Okay, so this is something that I want you to understand. You didn't probably was not very conscious about this equivalency. Neither do I. I just realized that. I haven't checked that, but I'm 100% sure that this equivalency will work. Okay? Because I didn't need calculations to understand this equivalency. But if you want to write it completely formal, of course that would be the case. Okay. So we learned that so this is now our question. We have RA is equal to 0 and we have R not equal to 0. I want to prove that the capital A is equal to 0. What I want you to understand is this. I want you to understand proving the truth of this implication makes the problem done. Even though this is written slightly in a different way. The problem is written in this form. The problem is written is that if this is equal to 0, then R is equal to 0 or A is equal to 0. The statement that you see in the problem is of this type, but I am claiming it was very evident for us that these two are equivalent. Please check that as an exercise in logic. And then instead of proving this, I prove this, which is this one. And now it becomes clear. Because now RA is equal to 0. Oh, sorry. RA is equal to 0. And I know that 1 over R exists. Why? Because you are telling me that R is not equal to 0. I multiply everything by 1 over R. And on the right-hand side, I can use that property again. On the right-hand side, I can use the property that the number by the 0 matrix is the 0 matrix, and then I get 1A is equal to 0, then this gives me A is equal to 0. You see, I am just giving these proofs not because they are hard, because I want you to understand these details, because this is a mathematics specialization course, so I really want you to understand these things. Okay. So if I want to solve this, now I have everything at my disposal to solve this. And then because the properties of addition of matrices, the properties of multiplying a number by a matrix, all of them are exactly as we expected for numbers, so no worries. We just pretend that these matrices are numbers and then we just go forward. So if you want to solve this system, what do you think is a good option? We need to use, for example, addition method, yes? So I would say that I multiply, for example, the first one by 4, the second one by minus 3. So then what happens? It becomes 8x. So I justified that everything that I am doing is legal, yes, mathematically legal. So it is 12y is equal to, on the right hand side I will have 4, 8, 12, and 0, and then I multiply the other one by minus 3, it becomes minus 9x, and then I will have minus 12y. On the right hand side I will have minus 3. Please correct me if you see I'm making mistakes. And then I add these two side by side. This becomes minus x. 12y and positive 12y are gone, and if I add them it becomes 1, 2, 9 and minus 3, and then finally I get my x. X becomes minus 1, minus 2, minus 9 and positive 3, as simple as that. And I put this x into one of these equations, try to find y. So this becomes 2 times x, which is minus 2, minus 4, minus 18 and 6 plus 3y is equal to 1, 2, 3, 0. But you learn that I can move. The price that I have to pay is to change the sign, so it becomes 1, 2, 3, 0, minus, minus 2, minus 4, minus 18, 6. So let me simplify this. It becomes 3, 6, 21, minus 6. But I want to find y. I divide. Don't divide. I multiply by a third. Yes, so this becomes 1, 2, 7, and minus 2. So this is a matrix here, and this is my matrix here. And finally, the last point of the lesson today, we still have 5 minutes. That is a nice definition in linear algebra. It's called a linear combination. It's just a very simple terminology and very useful when we deal with linear algebra. So if you have a bunch of matrices, whatever you like, if you multiply them by some numbers and you add them, definitely you will get a new matrix. This matrix is said to be a linear combination of these matrices. So that's just a terminology. Yes? So if you have a bunch of matrices, you multiply them by some numbers and add them together, you get a new matrix. That new matrix is said to be a linear combination of these matrices. And the numbers sitting here, the numbers that you have used here, are called coefficients of this linear combination. For example, assume that this matrix is A and these two matrices are E1 and E2. It is very simple. You can check it yourself. Multiply this by 2, multiply this by minus 5, and add them together. You will get this matrix back. Then you can say that matrix A is written as a linear combination of E1 and E2, and if someone asks you what are the coefficients, they mean that tell me 2 and minus 5. As simple as that. And let me solve the last example and then we are done. Write this matrix as a linear combination of the following matrices. So what does it mean? It means that write this matrix minus 3, 4, 2, and 0 as a linear combination of these three matrices. So it means that you can choose a number, let me call it x, multiplied by 0, 1, 1, 0, multiply the other matrix by a number y, multiply the other matrix by another number, for example z, and try to fine-tune, if possible. Sometimes it is not possible. If it is not possible, you would say that this is not possible to write this as a linear combination of these matrices. So you just write x, y, and z and try to fine-tune them so that this equality holds. And that is very simple exercise, yes? So what you do, you just repeat the left-hand side, and then you multiply x inside, multiply y inside, and multiply z inside. And on the right hand side you still can collect all of them by adding them. So it becomes minus y component wise, x plus y plus z, and 0. Am I right? So 0 minus y and 0 is minus y. X plus y plus 0 is x plus y. X plus y plus z is this, and 0 plus 0 plus 0 is this. And then this means that if this is going to match, then minus 3 should be equal to minus y, 4 should be equal to x plus y, 2 should be equal to x plus y plus z, and of course 0 is equal to 0 is trivial. So from this equation I get y is equal to 3, from this equation I get x equal to 1, and from this equation I get z is equal to -2, yes, because if I put x equal to 1 and y equal to 3. But the answer that you need to provide are not x and y and z. You have to write it down for me. So it means that I have asked you to write this as a linear combination. So this means that I got x equal to 1. Of course, if you want, you can ignore writing this 1. That is not a big problem. -1, 1, 1, and 0. And the next one is negative. You can write plus negative, but I would prefer to write just negative. I mean, this is the answer that you have to provide at the end for this problem. Let me make it better. Okay, so that is it. Any questions? Yeah, we are right on time, so see you in Math 5 in a few minutes. Bye bye.